list of people as they roll in the introductions. Please be sure to add your name there so we can add you to the list of participants. We want to make sure we represent everyone that was here in our notes. I am seeing some less familiar names, so what I'd like to do is a quick introduction to the IARPIC before we get into today's presentations, just so you have a little background, you know what we're about. First, I'm Mike Brady. I'm IARPIC Data Team Co-Lead. This is the IARPIC Data Team. I'm also a cartographer with the Department of Defense and National Geospatial-Intelligence Agency. Co-lead Jonathan Blythe is here as well. We'll let him introduce himself soon. Just a little background on IARPIC. So the Interagency Arctic Research Policy Committee, IARPIC, is charged with enhancing scientific monitoring and research on global environmental issues in the Arctic. The IARPIC established the virtual IARPIC collaborations, this virtual space, to connect federal and non-federal government researchers and stakeholders to address hard problems defined in the IARPIC 5-year plan. And do you have the website to the IARPIC plan update? So many of you know the IARPIC is currently updating its 5-year plan. And they're currently so federal teams have gotten together. They're currently writing the updates to the plan based on public input. And the next opportunity to provide input is going to be through the public review. So expect that in early 2021. And that's for the next 5-year plan starting in 2022. Okay, you can pull that down and get back to my notes here. Thanks again. As a reminder, so the IARPIC collaborations, as far as the structure, the data team is a sub-team to the environmental intelligence collaboration team. So with EI, we tend to gravitate towards use-inspired science perspectives for policy and decision support. So as such, we use this platform as a way to voice scientist, practitioner / user co-production approaches. So those scientists and practitioners working together, the focus on enhancing Arctic data access and usability for decision support, policy support. So that said, the two presentations that we have today are perfect examples of that scientist-practitioner collaboration. We have Dr. Macarena Ortiz. She will present on work done by scientists at the National Geospatial-Intelligence Agency on advancing methods for sea ice mapping to address operational needs. And she'll be followed by Ms. Alexandra Darden. She'll provide an overview of the National Ice Center, which of course provides maritime decision support. That's all I have for intro. Jonathan, did you want to introduce yourself and add anything before we get into presentations?
Hi, everybody. I'm looking forward to this meeting. It's been a long time in coming, so I just like to get on with it. Thank you.
Great, thanks. So, yep, go ahead, Ann.
We had a number join starting with a 240, ending with an 857.
Hi, that's Evelyn Bowens from the NIC.
Thank you.
All right, let's kick it over to Mac. And I should say we'll try to get through we're going to get through the presentations without Q&A unless you have something burning. So Ann, if you want to bring up in those slides. And I should note that for the record, these presentations address IARPIC Performance Element 9.4.4 to advance agile situational awareness for decision support for Arctic operators. So if we have Mac's slides, we'll get rolling into presentations, and then we'll have about 20 minutes at the end for discussion.
Hey, Mike, actually, me and Alexandra said we'd rather switch. It just makes more sense that way. That's okay.
Well, it's your block of time, so we'll bring up the NIC presentation. Ann?
And the presenters will be sharing their own screens.
All right, everyone can see my screen, hopefully.
Yes.
All right, great. I'm gonna go ahead and get started then. I am Alexandra Darden. I am currently an ICE analyst at the U.S. National Ice Center, which I will give a little overview of who we are and what we do. So we are a tri-agency composed of approximately 50 uniformed federal civilian and contract personnel from the U.S. Navy, NOAA, and U.S. Coast Guard. Each agency recognizes the growing geostrategic importance of the Arctic due to the steady decline of perennial sea ice. Each has recently updated overarching policies and guidance that converge and agree, allowing us to freely accomplish the U.S. National Ice Center mission. The Chief of Naval Operations Outlook for the Arctic was released in April 2019, but the U.S. National Ice Center is the sole command explicitly named for its important contributions to the Arctic domain. NOAA's Arctic Action Plan was released in 2014 and is central to supporting White House strategies formed at the time to advance U.S. security and stewardship interests in the Arctic. And also in April of 2019, the U.S. Coast Guard released its new Arctic Strategic Outlook, declaring that the U.S. Coast Guard maintains the enduring responsibility for the national security and economic prosperity of the Arctic. The strategy notes the increase in demand for Coast Guard leadership and presence in the Arctic with plans to meet that demand. USNIC was also explicitly named as a key partner in the Arctic. With a global area of responsibility, the U.S. National Ice Center is the foremost government provider of snow and ice information. Being the exclusive source of snow and ice products for U.S. government customers operating in and near ice-infested waters, we produce a variety of snow and ice products, from the strategic to tactical scales designed for a wide range of customers, including, but not limited to, the general public, military planners, intelligence agencies, and the maritime and research communities. So in order to accomplish our mission, we first produce a set of routine daily and weekly products that characterize the state of ice and snow around the world. We then exploit this information to provide tailored and integrated support to our customers. So before we can analyze snow and ice conditions, we must first see the snow and ice. Our greatest resource is foremost our access to satellite imagery. Although we use a variety of satellite products, both domestic and foreign, active and passive, we rely heavily on synthetic aperture radar imagery due to its ability to penetrate clouds and provide reliable, high-resolution images day or night. We also rely upon in situ information provided by either buoys or from analysts that we routinely deploy aboard ships operating in the sea ice. And finally, especially for a characterization of snow cover, we use a variety of surface observations, for example, weather stations and webcams, and also weather radar. We leverage these raw observations alongside two areas that are increasingly expanding their capabilities: machine learning algorithms, which some of which will be talked about later by Mac, and modeling. Some of our partners have begun to provide us with information, for example, sea ice motion derived from satellite imagery, and we have long used models from US Navy, NOAA, and Canadians to assist our analysts in creating forecasts. So as mentioned previously, we create a number of regularly scheduled products. Daily, we characterize the extent and concentration of sea ice and create a snow-no-snow maps for the entire globe. Weekly, we characterize the stage of development or thickness of sea ice around the world, as well as a more detailed concentration. We then exploit these characterizations to tailor products to the particular needs of our customers. For example, we regularly produced high-resolution sea ice information designed to assist customers navigating in or near ice-infested waters, such as icebreakers or research vessels, classified information detailing fractured sleeves and planias in the ice for U.S. Navy submarines, and information tailored to assist the deployment of limited U.S. Coast Guard assets over a wide geographic area. On top of our scheduled products, we also have many tailored support products that occur throughout the year in the Arctic and Antarctic. I'm going to focus on two the USNIC regularly supports in the Arctic, starting with one for the Arctic Submarine Laboratory, also known as ASL, with planning and operational tools for their biannual ice exercise referred to as ICEX. USNIC leverages imagery and model resources along with ice analyst skill sets to determine ice type, estimated ice thickness, and to predict the movement of ice flows. This analysis helps ASL find an ice flow from which they can build an ice camp to command and control a multinational submarine exercise. The product shown on the screen is annotated synthetic aperture radar, where an analyst has identified candidate multi-year flows for the ice camp and labeled them with alphabetical letters. Analysts will track these flows from each satellite pass and determine their predicted drift and ice characteristics. The green arrows show forecasted drift and direction speed via the direction and length of the vector. Arctic buoy data, which you can see some of in the top left corner, shown as color-coded dots, is also overlaid on the analysis to show in situ drift rates. ASL is hoping to find a multi-year ice flow 6 to 8 feet thick, or 1.8 to 2.4 meters, adjacent to smooth first-year ice to accommodate an ice runway and submarine surfacings. This perfect flow must not drift more than 200 nautical miles away from Dead Horse, Alaska, or aircraft will not be able to reach it. In 2020, USNIC annotated imagery and forecasted drift rates led ASL to hone in on the region outlined in green. Flights were conducted over this area to survey the ice characteristics with the help of USNIC ice analysts and Navy forecasters to forecast ice position and aviation weather, as the Beaufort Sea is not normally covered by the National Weather Service. Throughout the planning phase of ISAC, USNIC provided zoomed-in analysis of the Beaufort region. This product shows a more detailed view of the ASL's region of interest. Aerial surveys and virgin landings on the flow marked R found favorable ice characteristics. And after 4 days of searching, flow R, which is seen in the center of this image, was chosen as the best location of the I-6 2020 ice camp. USNIC personnel were deployed to the Arctic and provided situational awareness of the condition of sea ice flows, such as this product, in the area, as well as tailored ice support as submarines are navigating beneath it. For the remainder of the exercise, USNIC provided daily regional Beaufort Sea annotated imagery, as well as daily zoomed-in analysis of the flow R seen here. The red outline shows the actual flow on which the camp was built and the associated buoy that was placed nearby the camp. USNIC also annually supports the U.S. Coast Guard cutter HEALY science missions with tailored support products and onboard analysts who provides real-time ice analysis and forecasting for efficient and safe navigation in science initiative planning. Time on board the USS's only medium icebreaker is expensive, so having a USNIC ice analyst allows chief scientists and crew members to most efficiently use their time. The annotated imagery on the left of the screen shows how USNIC provided imagery can be used to help plan routes via the most efficient and least resistant path through the pack ice. USNIC analysts on board are crucial in giving science and HEALY crew additional resources and are a bridge in communicating with the USNIC while everyone is focusing on other tasks of the mission. So before turning over to Mac, I want to talk about by joining this collaboration with NGA, the USNIC can explore the possibility of using machine learning to ascertain current ice conditions. If USNIC analysts were quickly able to acquire current ice conditions and ice thickness for at the very least these special support missions I just talked about, more time could be spent on forecasting and outlooks, as well as providing a quicker turnaround of ice analyses for short fuse requests and decision making. So that concludes my brief. At this time, I will turn it over to Mac for her presentation.
Thanks, Alexandra. So as quick comments for those that are online, sort of draw your attention to the draft or list of example questions in item 5 on the agenda. So as you're hearing these presentations, think about the questions you want to ask in the discussion at the end. Over to you, Mac.
Great, thanks. Thanks, Alexandra. Can everybody hear me?
Yes, and slides are good too.
Awesome. Okay, so good afternoon. Thanks everybody for joining. My name is Macarena Ortiz, and today I'm going to present a follow-on to Alexandra's talk on how NGA and the USNIC are collaborating on a project which uses automation and machine learning for ice mapping. This particular project has been a partnership among cryosphere scientists, mathematicians, computer scientists, and physicists. So although a variety of satellite sensors are used for sea ice mapping, one of the most prevalent sensors used are synthetic aperture radars. The reason why SAR is so widely used, as Alexandra mentioned, is that no solar radiation is required since this is an active sensor and it uses its own source of illumination. So we're able to image over the Arctic and Antarctic regions during winter months where little or no sunlight is available in those areas. We also know that the Arctic is a very cloudy place, especially during the summertime. So, you know, SAR operates at a particular wavelength where it can penetrate through clouds. SAR sensors have the ability to send energy to the ground in different polarization modes, and different ice types in the ocean surface can be seen through these combinations. And finally, most of the SAR sensors are polar orbiting or near polar orbiting, and so we get excellent coverage in those areas. So how does SAR actually work? Well, SAR is a radar for rough surfaces. If we start with the figure on the left-hand side, SAR sends pulses of energy to the ground depicted by that transmit arrow. If the surface is very rough on the ground, the pulses of energy will interact with that surface and be scattered about. So by the time that the satellite sensor has moved just a tiny bit in flight direction, the signal received will be a sort of a sum of the various rough materials on the ground and will look very bright in the SAR image. Now, on the other hand, on the right-hand side, if the SAR image is over a very smooth surface, like a calm body of water or a paved parking lot, that smooth surface acts like a mirror. And instead of scattering the energy in all directions and back to the receiver, those signals essentially get scattered directly away and the signal is lost. So that part of that image will look very dark. And you know, there's a lot more to SAR and how it works, and I urge you to do some research about it if you're interested, but we can't really cover all of that in this presentation. So this is a comparison of a SAR image on the left-hand side, and on the right-hand side is a panchromatic. And these images have been taken very close to one another in the Beaufort Sea, and I mean close to one another in time and space. They both have very similar resolutions. The optical is close to 1 meter and the SAR is about 3 meters. I just want you to notice that the SAR on the left-hand side, the calm bodies of water are very dark, like I mentioned before, and the ice specifically over the ridges are very bright, and that's because the ridges are very chunky, so therefore the materials there are rough. And you can see a lot more structure with the SAR. The ice ridges pop out more, and you see much more different shades of gray as opposed to the optical. However, in the optical images, it's a great use for studying things like melt ponds. So for our work, we used data sets coming from the TerraSAR-X and RADARSAT-2 imagers. The RADARSAT-2 images were used in wide ScanSAR mode. So, you know, RADARSAT-2 is going to give you a larger area coverage, while the TerraSAR-X, which is in strip map mode, has a much higher resolution of about 3 meters, as opposed to RADARSAT having 50 meters. The TerraSAR-X can give you a lot more higher features and higher resolution features. So our goal for this project was to segment pixels in SAR imagery into ice or open water. And we wanted to do this in an automated way. So we tested out 2 different types of machine learning techniques. One was a supervised method and another one was unsupervised. So for those that don't know much about machine learning, supervised methods require labels while unsupervised methods do not. For our supervised method, we decided to use a specific convolutional neural net called UNet. And for our unsupervised method, we used a variational autoencoder, which we then fed into a clustering technique. And I'm going to get into more details about these in the next slide. So for the UNet, we used 130 labeled RADARSAT-2 images from a data set in 2014. The labels were ice, no ice. If the ice was very, very dark or dark gray in the labeling process, we attribute this as open water. Also to note, we used real backscatter values from the radar as input data. So the graphic you see below shows how a test image on the left-hand side, an image that the neural network has never seen before, gets segmented into ice probabilities. And these pixels are yellow in color, are more likely to be of class ice, while the pixels in deeper blue are more likely to be open water. There were some processing steps I'm not showing here, but for the sake of time, but in essence, because UNet works by feeding chips of images to the classifier, the ice probabilities came out rather blocky in appearance. So that we had to do was average several offset of outputs of ice probabilities together so that we can get a smoother probability prediction. So people don't want a probability image, right? They want an ice, no ice binary image. And so in order to do that, we took our ice probability images, outputs from the CNN, and we thresholded any pixel values that were above 0.5 in the probability space to be ice, and anything under 0.5 to be open water. And then here you can see that the sequence of the original inputs are images on the left, the ice probability intermediate output is in the middle, and on the final binary output is on the right. So we wanted to know from an analyst perspective how well our ice maps were performing. And so we partnered up with the US NIC, and particularly with Alexandra, and she gave us some feedback on the performance of the model. And I'm gonna leave it to her to explain some of that on the next slide.
All right, thanks, Max. So the binary image, sort of seen here, it's a little covered up by the ice concentrations, but it was created from a RadarSat-2 image from the Sea of Acos in February of this year. To understand how well the binary mass did picking up ice from the RS2 image, I overlaid the original RS2 image in the binary image. I then analyzed the image at the same resolution I would if I were analyzing a US NIC looping chart that I talked about earlier to understand how well the binary image did compared to an analyst's average analysis. So you'll see at the top an attribute table that's associated with the different colored polygons on the slide and some comments associated with them. Overall, it did a great job picking up unconsolidated ice seen in the pea green, or what I see as pea green, color that makes up most of the image. If you go back to the previous slide, though, we notice within the consolidated ice, it's indicating openings, and to the untrained eye, they appear to be ice-free in the RadarSat-2 image. However, they have already frozen over with new ice or ice less than 10 centimeters. However, it does extremely well on picking up on the detail of the ice tendrils or ice extending from the main pack ice in long strings in the central part of the image. So if Mac, you go back to the previous slide, so kind of the central part of the image is where it was doing well picking up the ice tendrils. So while this was to give us a quick idea of how the model is performing, the supervised training that Mac has been and will continue to talk about will allow for more accurate and higher resolution features that the US NIC can then utilize for their analysis. And back to you, Mac.
Thank you. All right, so we also experimented with some unsupervised methods, as I mentioned before, where effectively no labels were used. We used a combination of something called a variational autoencoder, which essentially learns salient features or the most important features of a data set by sort of compressing and decompressing the data and later feeding this into a clustering technique, in which we decided there would be 10 classes of ice types as an initial experiment. And we did this for RadarSat-2 and for TerraSAR-X images. And as you can see here, we basically trained on 70% of the data of the SAR images, and we tested on 15% of the data sets. The salient features we learned from the variational autoencoder were fed into a clustering algorithm using k-means. And as you can see here, we used principal component analysis to remap the clusters into a lower feature space. In the figure in the middle, you can see the 10 clusters. We found that this method worked best on higher resolution images like TerraStar-X, which has that 3-meter resolution. You can see that the resulting segmented image on the right-hand side, the orange pixels seem to be assigned to frazzle eyes. Calm water is assigned to that green cluster, and the blue pixels seem to have picked up areas of higher wind speed over open water. All right, so I wanted to briefly touch on a new project that we just started to develop at NGA with the NIC. And we found that altogether, the US NIC finds the automated ice maps quite useful, but they really want more control over the machine learning models. For example, they would like to do retraining on the fly. So we came up with an idea for a machine learning tool that requires a sort of a human in the loop in order to meet this need. The human in the loop is otherwise known as like a human machine teaming effort. So this tool incorporates active learning techniques. And let me explain how this works. An analyst would ingest a new image into the tool and where the image is pictured on the left-hand side. And let's say that for whatever reason, they didn't like the output of the ice map because let's say there were some errors. Through active learning, they can retrain the model on the fly without having to label a bunch of pixels, because active learning essentially presents the user with the most out of sample pixels, or the pixels the machine found the most difficult to label. And that's shown in that little red box all the way up on the left upper hand corner of the original star image. So therefore, an analyst that would only need to label pixels in that box as opposed to the whole image or a much larger portion of the image. Then in that specific chip that is presented by the active learning process, the analyst could be assisted to label by incorporating either clustering techniques shown by the k-means patch image on the sort of in the middle and the lower hand side, or they could use their weekly US NIC products. So essentially taking advantage of weak labels. So there wouldn't be pixel by pixel labels, there would be something like weak labels. And we're still trying to assess how viable that is. But we're very excited about this project because we're now working directly with Alexandra, who will be testing this tool as we develop it. And she's going to help us make sure that the tool stays relevant to the US NIC's workflow, and also help in providing feedback so that the tool gets things right in a variety of imagery. So no pressure to Alexandra at all. Okay, and finally, this is me recruiting you. We have several programs at NGA, and as you saw, we have pretty exciting research programs to work in, and we hope that you'll reach out and for collaboration and other opportunities. So with that, that's the end of this briefing. If you have any questions for me and Alexandra, please feel free to ask.
Thank you so much, Mac and Alexandra. Obviously, this is a great example of collaborating. You're innovating, developing science, and you have the National Ice Center that provides, obviously very important national service and, a lot of work to do, and not always, the adequate resources. So the fact that any effort is paid to being involved in the development of their own decision support tools, especially at the edge of science, I think is profoundly important and a very good example. So I appreciate you guys getting through a lot of content. I love the tag team style of presentations. Obviously fits well with the theme here of user-driven science. So I thank you for that and getting through it swiftly. We do have, am I seeing the time right? A half hour of discussion and roundtable, which is terrific. So thank you so much for being efficient with your time. Again, so the questions that we proposed in item 5, this is a collaboration space, right? So I always tend to look at the list of participants. I like to see, the scientists and those kind of working more in the practitioner space, like the National Ice Center, show up at these meetings, because to me that's an important performance measure when we're talking about collaboration for especially decision support tools. So the questions that are listed in item 5 on the agenda there, if you're looking at it, basically it's about the value added through these kinds of collaborations, and then related issues like how does that impact access, mission impact, and so forth. But obviously questions we can open up to technical within the scope of what was just presented. So that said, please join the discussion. We'll open the floor up to questions. Again, technical within the scope of what was just presented. Keeping in mind this is a collaboration space, so also a big picture. What is some value add and also opportunities for collaborating across scientist-practitioner boundaries?
Hi, this is Florence at the National Snow and Ice Data Center, and I just want to say I want to applaud the idea of the human-machine teaming, that approach that you're taking, because as I'm sure you're aware, there's been work over many years to do supervised or an unsupervised classification of SAR imagery, and it hasn't ever, to my knowledge, resulted in really robust results. And it's always seemed to me that it would be a whole lot more cost effective simply to put a human in the loop, speed things up, but have a human in the loop. So that's my comment. I just commend you for that, for jumping to that approach.
Thank you. Yes, I've been doing this kind of research for about 10 years now, and I completely agree with you. SAR, first of all, using SAR is hard already, and adding to that sea ice in SAR is even worse. And as we know, sea ice tends to look very different in seasons, and where and the ice if it has different temperature, or if it just got slightly wet. These models are best, as you mentioned, having the human in the loop for applying more robustness to the technique.
Yeah, the signatures overlap a lot. The other thing that can help, I don't know how often this is possible, but if you can bring more channels or more of the spectrum into play. I guess if you just got one single channel image, there's not much else you can do, but it all depends, I guess.
Yes, definitely more polarizations. We're aiming to add that to our data sets.
And if you don't want airtime, feel free to throw your question into the chat box and we can get it, insert it into the conversation for you. We do have, I see some names here. I don't want to put anyone on the spot, but those that do, their job is working across these boundaries, those kind of more domain awareness focused individuals. So comments about the working together across these agency boundaries, welcome. One in particular is something I'm really interested in is, and it's good that we have National Ice Center that I think maybe you'll speak to this, is we're doing this work for primarily decision support to development, but I have to believe that those efforts could potentially also be relevant for addressing knowledge gaps. So what is the relevancy of these observations and tools for knowledge? And that gets into the, we discover what each other are doing. There might be opportunities to economize and get value from each other's equities. So I'd love to hear from scientists. What is some of the, you've heard questions about some of the big topic here is dissemination of data, access to that. Hard to do, so oftentimes definitely hard to do if it's not required or vocalized as a need. So that's what this space is there for, is to develop networks. I don't expect it all to happen here, but hopefully some emails get exchanged after this meeting, and that's the kind of impact we're also after. So anyone willing to that wants to comment on the idea of addressing information in addition to or knowledge in addition to information needs, please speak up. So we do have a couple questions coming up in the chat box. So is there a way to use surface ice observations images in the ML process? Not sure who that question is directed to. ML process, can we define ML?
Machine learning.
Machine learning.
Thank you. So is there a way to use ice surface observations images in machine learning processes?
So like ship-based measurements, I suppose.
Yes, you mean like temperature and humidity and wind speed and that. Yeah, that would be ideal. Unfortunately, right now, because for example, like the RadarSat-2 image is 500 kilometer by 500 kilometer image. That's a huge area. If we were to attribute any point measurements on an image to an area that large, I would be concerned to using that kind of information. However, in a more high resolution image, like in the TerraSAR-X example, we could definitely use something like wind speed. And perhaps if you're doing a flow-by-flow analysis, that would probably be appropriate for that. Yeah.
Any follow-up there? Thanks, Mac. So a question about access. So what are the current US licensing requirements for RadarSat-2 and TerraSAR-X? So the issue of, university researchers potentially can benefit from that, including the customers they serve, human knowledge. What's the story there with access to that imagery?
So right now, the RadarSat-2 and TerraSAR-X, we have agreements with the RadarSat-2 specifically. We have agreements in NGA to get data sets, which we purchase. So they're not free, and the TerraSAR-X as well. So universities, well, if you have an idea, if you want to reach out to me, we certainly have ways that we can share the data through something called a CRADA process. And I can get into that in more details at another time, but it's basically an agreement between NGA and a university, and we can exchange ideas, algorithms, and data sets. And there just has to be specifically to the project. And certainly there's room for us to be, able to share the RadarSat-2 and TerraSAR-X imagery that way.
Thanks, Mac. Another question, so about dissemination and access related, are digital sea ice products available in other than GIS format? So I guess not.
Are you talking specific, like what we currently produce at the USNIC? Are they available in other formats?
I believe that's the question, yes.
Okay, we do have Rainform Gold format. We also have ASCII files. Is there a specific file type you're looking for?
So Igor, if you have ideas about other formats.
Well, it is just regular concentration and sea ice type. Weekly maps for years and years collected in National Ice Center archive. Just concentration, because users want gridded data, for example, and they don't have access to GIS system. There is a question. It used to be available.
We also have graphics, but unfortunately our data mostly is in GIS format.
Yeah, I can help a little bit with that. I think this is Florence at the National Snow and Ice Data Center, and we're working with USNIC now to archive some of your products and get some of them into a gridded format, and those include the weekly analyses that you do. So there's a there's an older version of that gridded version of the sea ice analysis charts online now with the concentrations in a gridded format that Igor's asking for, but it only goes through 2007. So before the end of the year, I hope we're going to get the updated version of that out. I also put in the chat box a link to a website at NSIDC that has the marginal ice zone analysis, the daily marginal ice zone analysis that USNIC does. It's yellow. I think of it as the yellow and red product that shows the marginal ice zone 10% to 80% in yellow and then greater than 80% in red. But that's the first one that we've worked closely with USNIC to document and get an archive and get online. So I encourage everybody to check that out. That includes the user guide, which is our documentation, includes some information at the end about other products that we're working on and that we already archived for USNIC. And oftentimes the reformatting is one of the things that we do just to make the data more broadly usable by a wide community of researchers who, like Igor said, are often not used to working in GIS format.
Thank you, Florence, for stepping in for that.
I'll just ask my question if I can.
Please.
Yeah, so I may have missed this because of things going on in my house with education at home and whatnot, but so what I caught, I wasn't clear if this was yet like operational and you have the ability to respond to events or emergencies, and how latency can be addressed. Say if you need information a couple hours sooner, is there a way to speed up processing?
I'll pitch in first, and then Alexandra, if she wants to say anything about that. So the way that the algorithms work, they're pretty fast. The training was on one GPU. It took 36 hours for the ice, no ice. But for the active learning, because it's going to be, you're essentially just taking one image. It's a matter of maybe minutes that it trains on. So there's no really lag time in that. As the part of it, affecting emergency and response efforts, I can't talk on that. I'm not sure if Alexandra wants to take that one on.
Yeah, so I mean, the latency would really be coming from the imagery latency. And so as soon as we get that, we could run it if we have the machine learning tool at that point, or we would just use it as analysis. So like Mac was saying, it would take a few seconds to run it through. So I can't really see that being an issue at this moment. But it's still in the, I guess, it's not operational yet. We're still trying to work on it.
I guess that's what I missed. Yeah, because it'd have to be somehow brought into the ground system for that satellite data. And especially interesting imagery, you'd have to be able to order it, maybe with some, with some latency associated with that.
Right. So with RadarSat, we do have the ability to place emergency orders. Obviously, it will cost more. So we try not to do that, but we can do it if necessary. And then we would just take that RadarSat image and run it through.
Right, so not seeing any, thanks for that question, Jonathan. Not seeing any questions in the chat room. I do want to ask a question about your experience working together. So this idea of co-production, the users working with producers is not new. It's a prominent theme also in science circles, and it's a known challenge to really effectively engage your users, especially when you have lots of users. In this case, the user is very clear, and you have a statutory mission. It's like a little bit, you're working within kind of good constraints that facilitate close collaborations. I'm not saying it's easy. That's gonna be my question, is what's your experience there? What's the value of putting your effort in there? But I think the lesson, like more broadly, is what we see out of this more kind of closed interaction system where this is a statutory mission. You got to have the information for mission support, and no real decisions there. But the methods by which you do it, it's kind of a really good example that could be embraced more in the science community. Scientists do great work in that regard in many ways as well. But that close kind of interaction is tough to do, especially scientists are often dealing with a range of stakeholders. So first of all, is this common at National Ice Center? Is this like how products get developed historically? And how well has this collaboration been going? And your view on the importance of it? Is it worth spending the additional effort to interact? I know it's not easy. Is it worth it? Is it going to be a better product in the outcome, better mission support, et cetera?
So usually I think this has been fantastic so far. It's been really easy working with MAC and NGA on this process. We've only been doing it for about, before we kind of officially agreed to this, we kind of been off and on for about a month, but now that we have an official agreement going, it's been a lot easier just having those communications. I am not aware of if we have done anything like this before. Usually researchers kind of, from what I understand, develop something that they think might be useful for us, and then we kind of get the end product and see if we like it or not. I think this is great because, I mean, we're going to be the ones using this in the end. So the fact that they're allowing us to have a role and say what we want as the end product, I think is fantastic and absolutely worth our time and effort.
Thanks, Alexandra. Yeah, I would say that I don't think this project could have developed without the collaboration, especially for this tool, because some of the scientists that are working this may have an idea that this could work this way, and we want it to be this other way, but essentially it's not useful for the analysts. So that interaction is critical, especially for anything that has to do with the human in the loop, and even just asking questions about computing resources at the NIC, right? We have to know like what kind of computers they have, what kind of software restrictions they have. So that all actually has to get discussed. And we're hoping that along the way, we don't just discuss the science behind it and the robustness of it, but also like the ease of transition and the competing needs and their software needs and all of that.
That's terrific. Sounds like a best practice to me. And at NGA, we say show the way. So it's good to see it happening. It's hard to do. So thank you all. I know probably others involved too, but thank you too for presenting and representing this important work. I do want to start shifting focus. We can, still take questions as they come, but ideas for future presentations also welcome. In particular, again, Jonathan and I are trying to create a platform where we bring in practitioners into the conversation around science. Not oftentimes practitioners, they're busy doing the work they have to do. They're not always able to come to these meetings, but we believe that if we do a little extra work getting individuals like Alexandra from the National Ice Center into the conversation, then there's value to be added there, and we're willing to put in that additional effort. So I guess that's my way of leading the conversation on future topics, but I do want to open it up for others that, not necessarily on this topic, but ideas for future presentations they want to hear out of the IARPC data team. And just in case we didn't get, ideas out front, we did plant one in the audience. So I'm going to ask Ann to bring up Mark's slide. And Mark, if you could do a brief introduction and your ideas for a future topic.
Yeah, for sure. So I don't know if I have any Canadian colleagues on the line. I don't see the list, but if I do, good day. My name is Mark Stoddard. So I'm a scientist with an organization, an agency called Defense Research and Development Canada. So we're a bunch of federally funded scientists who work primarily for our Department of National Defense. My lab is in Halifax, Nova Scotia, where we work primarily for the Royal Canadian Navy. We also maintain permanent facilities in the Arctic, one on Devon Island, which is about 100 kilometers east of Resolute Bay, and a permanent footprint at CFS Alert, where we conduct a lot of our high Arctic research. And we've been doing that since about the 1940s, 50s. The motivation I'm going to get to here is for anybody with an interest in international shipbuilding. The Royal Canadian Navy's finally taken delivery of its first hull of a new PC-5 Arctic offshore patrol vessel, and this is the first of 6 that'll be delivered by about 2024. The interest here is that one of their primary missions is presence and science missions in the Arctic, yet to be defined. So there's a big interest in it. It was fitted for, not with, science payloads. So a lot of the work at our lab now is trying to understand the questions these ships can help us answer, the types of technologies that we need to develop to take best use of this physical presence in the Arctic. One of the questions that's been asked really early on is to assess the ability of these new vessels to generate operationally relevant maritime domain awareness. I think all of us are aware that maritime domain awareness in the Arctic specifically is predominantly generated from space-based sensors and systems. The big question here is what value are the high-resolution local point observations from these ships at the national level to maritime domain awareness? In order to answer this question, our lab has a long history in terrestrial sensing, shore-based and ship-based. Our space-based sensing is rather limited. We have some labs that look at that. So we chose very early on to partner and reach out to US Naval Research Laboratory, who obviously I won't talk about what they're experts in because everybody seems to know that they're the world experts in space-based sensors and systems, and definitely are leaders in maritime domain awareness related research. We've worked with them on a defense topics for many, many years. Our lab has a long history working with the US for defense-related issues. So we're really looking at Arctic MDA, specifically the contributions of ship observations at the national level, but we're also interested in improving Arctic navigational risk management. So these ships are relatively new to the Navy, so they're going to have to build a lot of experience of operating long duration missions in the Arctic. So this would be transits over very wide areas where they may encounter widely varying ice conditions, answering how do they manage navigational risk? How do they produce accurate estimated times of arrival for efficiency of movement? How do they forecast fuel consumption based on expected ice conditions? All of this trying to add a bit of rigor and analytics to the decision-making processes to do this. So right now we're in the process of developing unattended acquisition systems that can be placed on these platforms, and the data can be sent back remotely over SATCOM. We're looking at how the framework in which we will assess the contribution that these local sensor measurements are making to MDA. That's a big part in concert with efforts with the US NRL. And then looking at how these local observations could improve local risk management on the ship, whether that's through improving predictive products, or just how they can be used to improve movements of the ships. We still don't really know exactly where that'll go. It's very open-ended. The project arrangement's currently signed and funded out to 2023. So it's a long relationship, I feel, that has a lot of room to maneuver in the directions we want to take it, and that we have several activities ongoing. I'm not really going to speak to the slide. That's just there for people to take away. If they have questions, my contact info is there, and would be happy to talk to anybody who's interested in ship-based observations and how they can play a role in improving or enhancing Arctic maritime domain awareness. Thank you.
Thank you so much, Mark. Looking forward to talking about a future topic. One thing that comes to mind is when you're looking at risk, is it, where do you draw the line? Is it like, what's risk to the ship? Does it also include the risk to, local communities and their subsistence habitat, which obviously translates into risks that operators need to consider for a variety of reasons for their own maneuverability. So looking forward to talking more a bit about that idea of, addressing a broader needs through this maritime domain awareness mission lens. So thanks so much. Do have one, before we turn it to Jonathan at the end here to give you an idea of what's coming next for talks. Do have one more question here in the chat. Let me find it. And I like this question. National Ice Center, let me know if you want to take this on. So the question is, do you have other products that are not sea ice? So I think this is idea is like other products that are addressing things like river flood risk.
Yeah. So unfortunately, no, we don't do river ice. We do Great Lakes ice conditions, so concentration and thickness, as well as snow cover for the northern hemisphere. But yeah, no river analysis.
And you guys are busy enough, right? Keeping up with
entire globe.
Okay.
Understood. Thank you.
Thanks for the question. So, any other comments, reactions, questions before we start closing the meeting?
I'd just like to suggest a possible comment for a future meeting. One thing I'm always curious about is how the operational services predict ice, do ice forecasting, short-term ice forecasting, ice outlooks. So I think the more the science community could learn about that, the more we might be able to help.
Thank you, Florence. So Mac did provide our contact info. Please reach out and reach out to me as well. I can plug you into some other researchers that may speak to that issue as well. Thanks for the comment. Okay, so we're coming up on time, a couple minutes. I want to turn over to Jonathan to plug the next talk.
Okay, can you hear me?
Yes.
Okay, great. So thanks to the speakers for today. Very interesting talk. For next time, we're going to be shifting gears a little bit, but really not that much. The goal of the meeting is to focus on how different sectors in society, private sector, academia, government can all contribute analytical capacity and proprietary data assets to best advance the Arctic research enterprise. So more of a policy level treatment of the same topic we're talking about today. And but doing all this while protecting individual privacy and data sovereignty. And we'll have one speaker for this. His name is Gary King, who works at the Harvard School of Government. So stay tuned for the invite, which we're just wrapping up, and we'll send that out to the team later on this week or next week. Thank you, everybody, for attending.
Thanks, Jonathan. Thank you all. Mac, Alexandra, awesome work. Thank you for your hard work.
Thank you for your time.
Okay, take care, everyone.
Thank you.